Okay, so I'm gonna start, and so our topic today is, well, will be multiple concepts we're gonna go over. So one of them is we talked about the magnetic field of Earth. So and basically the topic is how magnetic field of Earth, magnetic field of Earth interacts with the solar wind. So it's kind of general question, and then we will look at different parts of this question. So let's see. I'm going to share the screen with you in a moment. I'm going to show you like something that usually we draw like for the magnetic field of Earth, right? And then we will see how it actually looks like. It's actually supposed to look like. So let's see. I'm going to put this here. This one. So I'm going to share the screen. So if you're looking at the screen right now, you should see on the right side the magnetic field of Earth. So idealized form of it is like a bar magnet, I like uniform bar magnet, and the field is symmetrical, right? There's nothing unusual here, very simple, right? And the other images may look like this, for example, or like this. So this is in case where Earth was a really perfect ideal magnet. The reality is it's obviously not a perfect magnet. Its magnetic field looks a little bit more complicated like this. Can you guys hear me? This internet connection is off. So
Yeah.
okay. So this is a more complicated shape of the magnetic field, right? But even this is pretty symmetrical. In the absence of anything else, this, it would look like this. And I should point out also that we don't quite understand how magnetic field of Earth is created. The idea is that some currents flow inside the core, and they generate magnetic field. The question is, where does the energy come from to maintain the current, electric currents within the core? There must be substantial amount of current there. So one of the ideas is that there's motion of particles, a flow of particles, especially in the molten part of the core, that is powered by radioactive decay. So Earth is made of obviously iron, but also the radioactive decay of heavy elements like uranium or thorium. They should be in the core in larger quantities that they're found near the surface. So they, as they break down, they probably release energy and power the whole process. But again, we don't quite understand how it works. At least I don't quite understand how it works. And we just know it exists, right? Some planets don't have magnetic fields. Moon, I think, does not have magnetic field. And now, if you look at interaction of Earth's magnetic field with other fields, specifically with the field generated by the solar wind. Solar wind is basically plasma. And I'm going to actually write down on the screen, and I'm going to come back to this. So now let's type it here. Type. So solar wind is a flow of protons, primarily protons and electrons. So they fly at a very high speed. Electrons, right? Electrons, like that. Electrons. And they have at a very high speed. They're emitted by the sun, and they move in all directions, obviously. And Earth is one of the directions. And the solar wind will interact with our magnetic field. So And when we see this, I mean, we can visualize it, and we see that our field will be distorted. So it looks somewhat like this. There's a bow. This is due to the pressure of the solar wind onto the magnetic field. So magnetic field of the sun is pushing onto the magnetic field of Earth. Creates this shape. And behind that, behind the Earth, so like here, this will be the day side. You're looking, you're facing the sun. And the night side, the field will be more like stretched out. Okay, now most particles will deflect. So like if you look, say, maybe this image, most particles will come and deflect away, but some particles will be trapped. So also understand that magnetic field of Earth is gigantic. So tens of thousands of kilometers outside. And it also has like a complicated shape like this. It has multiple layers actually. And I think they call Van Allen belts or something like that. So what happens is the particles, most particles, they're coming really fast. They will just bounce off the field, right? So it's kind of protecting us from direct heat by those particles. Some particles, though, will be trapped inside, and we're going to draw that. We're going to see how this would look like. So let's say we're going to put here a sphere. So it's going to be pink Earth. And the line, magnetic field lines. So we know the field lines come out of this pole and they go here, like that. And obviously they come out from here and go like that. Okay, so again, here we have north, magnetic north, right? And here we have magnetic south. So let's say we have a charged particle. Let's make it a positively charged particle over here. And and it's flying, say, I don't know, this way. Mira, you have a question or connection problems? Mira?
No, I'm fine.
You good? Yeah, okay.
Yeah.
So it's moving towards the field like so. Okay? So we're gonna try to understand what kind of motion this particle will undergo in the influence at the in the influence or by the whatever when the magnetic field of Earth will affect the motion of the particle. So I'm going to have to demonstrate that. So you have to look at the screen. So on my screen, the particle is moving to my right. It should be the same thing for you. Can everybody see me? I can't see myself.
Yes.
Yeah. So if I point, the thumb will be pointing along the velocity vector. It's going to my right. I'm using 4 fingers to represent magnetic field, so it's going generally like in upward direction, which means the force on the charged particle will be going towards me at that instant, right? Again, you have to understand the field is quite big, so as the particle approaches, it will experience stronger and stronger force. In this case, the force is pushing the particle towards me, right, out of the page. Now, as the particle moves along the field, the force will change its orientation, so it will start moving like that. So now the force is now pointing away from Earth, or we can say to your left, to my left as well, right? So then this will force the particle to continue turning, and the velocity now is away from Earth, and the force is now pointing into the page, and the particle will then turn again, so it continues turning in circles like that. Is that picture clear? I'm going to draw that as well, but like the way you come up with that.
Yeah.
I guess I'm still a little confused as to why that happens.
Let's draw it. Let's see. And if it's not clear, I'm going to try to explain again. Okay, I'm going to turn off the video for now. So
Real quick, what does the
Yes.
thumb represent here?
thumb represents velocity. So you have to go back to the right-hand rule where we arrange fingers, digits along a particular directions. Thumb is velocity. 4 fingers. Let me turn the video back. So 4 fingers, because there are multiple fingers, you can always think of them as magnetic field lines, right? Multiple lines. The thumb represents velocity. You know, like cab, like that way. So that's a velocity, right? And then the force comes out of your palm. Okay, some people use this orientation, right? I'm more comfortable with that because 4 fingers resemble multiple field lines. That's the logic behind this rule. Okay, makes sense? Okay, I'm going to turn off the camera. So let's go here. So here we have velocity vector pointing this way, right? And what is that thing? The field line, let's say the field line is going this way. This will be B, and this will be V. Okay, is that clear? Like the picture itself? So I'm gonna move it here. Okay, so now we can resolve this vector into 2 directions. Right. Yeah, okay, so we're gonna draw 2 components. I'm gonna draw this component here. So this will be perpendicular component. It's perpendicular to the B, and this will be component of the velocity which is parallel to the magnetic field. Now the formula, if you remember, the formula looks like this: F equals Q, right? V cross B. So this are vectors, right? And cross product gives us a vector for the velocity. The component that will be affected by the magnetic field will be the perpendicular component, because if I want to find the magnitude of the force, that will be equal to Q V B regular product. I can actually put the absolute values here. Oops, B didn't work out. B like that, and here I'm going to put the sine theta. So for the perpendicular component, the angle is 90 degrees, right? So angle between B and the perpendicular component is 90 degrees. So this component will not be equal to 0. So for the parallel component, right? V parallel and B, right? They are parallel, obviously, and the angle between them is equal to 0. We know that sine of 0 is equal to 0. So parallel component will have no, the magnetic field of Earth will have no influence on the parallel component of the velocity. Is that part clear? Okay, that was long enough pause. So that silence means it's clear. So what happens is that the particles will move in this interesting way. The particle will go like that. And most particles which do get trapped in the magnetic field end up in the 2 polar regions. So near the south, geographic north, right? And geographic south. And we call these things Like here will be northern lights, right? Lights, or they also called aurora, which means I think shiny. Aurora borealis. Borealis. I think that's how we write borealis. So northern lights, borealis, right? And australis would be southern lights. Are there any questions about this? No questions. Amazing. So let me show you a few pictures. What am I? Where am I? Share the screen. Okay, if you look at the picture, can you guys see my screen?
Yeah.
Yeah.
Okay, so you see this like colors, all these colors are really interesting, and they come from about 50, 70 kilometers above Earth. This is where lights basically are generated, northern lights and southern lights. And you will see a lot of green light coming from that phenomenon, right? The green light actually was really helpful. People did not understand where green light came from, like these parts of space, like green light coming from regions, and then the spectrum of the light was not well understood. It was finally understood when people analyzed where this green light was coming from. Green light is coming from oxygen, and apparently oxygen is not allowed to have this kind of spectrum because at the density that it has, it's not supposed to produce kind of frequencies, and it's called forbidden lines. So the forbidden energy levels, and at regular pressure, it doesn't work. Okay. However, if the density of oxygen is very low, then this line can be actually be produced by oxygen molecules. Okay. Or atoms. I don't remember exactly atoms or molecules, but they will produce this particular color. Okay, so let's go back to the screen, whiteboard. Now I'm going to go to the next slide, and let's see how can we do this. Next slide. So basically, a particle could be described moving, following this kind of motion, like that. So can somebody, can you guys try to name this? Like, what would be the name of this kind of motion?
Spiral motion.
Spiral, okay.
Corkscrew.
True, okay, yes. Any other ideas? More like scientific?
Looks
Kind of like a spring, but I don't know.
Okay, any other, more like scientific? Biology maybe related?
Oh, helix.
Helix, yes, exactly. This is called helix. So we can actually write this that charged particles, they must be charged. If they're not charged, they won't be affected by the magnetic field. So charged particles undergo helical motion. The shape is called helix, and the motion is called helical motion. So this is helix, right? So like what's it called? DNA is double helix, and this is just single helix. So let me see if I can change this a little bit. Helical motion. So helical motion is the sum of parallel translation, right? And then circular motion. So you have a motion in a circle, which is due to the what's it called? Perpendicular component, right? So perpendicular component is the one that's making the particle to turn all the time. And parallel component is not affected by the magnetic field, so it just keeps on going. Now, if we go to back to the previous slide, this picture keeps on changing. So helix is not really straight, right? It's actually bent along the field lines. So particles then are pushed towards the polar regions. And then we have this, polar lines. Okay, so let's see if I'm missing anything. I got this, I got this, I got this, and this. Okay. Are there any questions about this?
Nope.
So using right-hand rule. You can put the question in the chat if you have questions, like. I don't see any questions in the chat box. Okay, so then we're clear on this. We're going to move on to the Google Classroom. And on Friday, I posted the questions. There was a worksheet, right-hand rule worksheet, and there were questions there. If you can go to that worksheet. So we're going to review the answers to some of the questions. Did you already take the quiz, by the way, electricity quiz?
Yes.
Okay.
Yep.
Okay, thank you. So can you all open that right-hand rule number 3 worksheet? So any volunteer to explain section 1, question 1. So here we're looking for the direction of the velocity. I mean, we're looking for the direction of the force, given that velocity and B.
I'll do it.
Go ahead, Hugo, right?
Yes.
Mhm.
So, you know that the X means it's going into the page. So
Mhm.
I took my 4 fingers and I pointed them towards the page, and then I lined my thumb up with a V, and I got down for the direction of the force.
Which hand are you using?
Oh, I never up. I accidentally used my left hand.
Uh-huh. So could you correct yourself?
Yes. Okay. Sorry. Point your thumb towards V, so that's to the right. Your 4 fingers are going towards B, which is towards the page. So your palm is facing upwards, which means
Upward, right? So the
direction.
force will be pointing outward. Does everyone understand this? Be honest again. If you don't understand, we can go with this. I can demonstrate that as well.
Can you go over it once more?
Okay, so let me try to demonstrate what Hugo was explaining. So let's see. Let me see the question. So basically, that's what we have. The 4 fingers pointing into the page. So I'm pointing them into the screen, computer screen, right? And that's where magnetic field lines are going. How do we know that? Because X there, right, that represents the tail of the arrow. And we're looking at the tail of the arrow, which means the arrow is pointing into the page. The thumb represents velocity, so it's pointing to the right. It should be the same thing for you, to the right. Then the force will be coming out of your palm, right? And in this case, it's pointed up the page. So always relate to the plane of the paper, or in this case, the plane of the screen. Do not relate to yourself, because your up or your left, your right may be different from someone else, right? But the plane of the paper, we're facing the same plane of the paper, so in relation to the paper, it should be the same. Even if I take the page, if I take a piece of paper and rotate it, right, its up will still be like if we keep this orientation, up will still be up. So it doesn't matter how we turn the paper, its orientation will not affect direction of the velocity of the force. I'm sorry. Does it make sense, Stella?
Yeah. Thank you.
Okay, no problems. Can somebody try to explain number 3? Any volunteer for number 3?
It would be out, right?
Which way?
Out. Like,
Out of the page?
hold on. Yeah,
Who's that, MD?
yeah.
Okay, could you explain a little bit more in more details?
All right, so use your right hand. The V would be the thumb. You point that up, right?
Mm-hmm.
The four fingers you point to yourself,
Mm-hmm.
and the center of your palm, the bottom of your hand, it points out towards your right.
You're talking about number 3, right? Okay, so 4 fingers point. Number 3, 4 fingers point to the left, right?
Yeah.
Is it right? And the
Yeah.
thumb is pointing up the page. Again, I'm
Wait,
relating
my bad. Towards you.
towards you, right? So the like that, right? So like
Yeah.
that, towards me, right? So if you relate to the plane of paper, it's going to be out of the page, right? So if I don't want to be too selfish, I won't say towards me, I would say out of the page, and there will be the same response to you, because like if you're on the other side of the page, you'll say, no, it's not towards me, it's towards you, which is me, and then it becomes confusing. So it's out of the page. Okay. All right, let's try maybe one more, number 5. Anyone?
Mr. Akhmedov?
Yeah.
Could you explain like how you got it coming out of the page?
Okay, you see what I'm showing, right? My
Yeah.
camera. So I'm related to the plane of my paper. You should be relating to the plane of your screen, the paper. So velocity is going up the page, right?
Wait, could you move your hand more? I can't see. Yes.
That you see it? I don't see
Yeah.
what I'm showing. So is it better?
Yes.
Okay, the thumb is pointing up. That's the velocity. 4 fingers go this way. That's the B, right?
And your palm is facing.
Palm is facing me, which is if I relate to the paper, the force is coming out of the page.
Okay.
Make sense?
Yeah. Thank you.
All right. Can someone try number 5? Okay, again, we're not looking for perfect answers. People make mistakes. It's important that you try. Try. If you're wrong, especially if you're not sure if you understand correctly, give it a shot. See if you get it. If you don't, you will.
May I
understand.
try?
Go ahead. Who is it?
Yeah, so this is Min-san.
Go ahead.
So the V is pointing towards the page, which means that your thumb is like to the paper. And B, your 4 fingers are to the left, so the palm would be facing upwards.
Upwards, yes, exactly. Let me follow that. So this is what I understand, and see if that makes sense. So the V is pointing into the page, right?
Mm-hmm.
Like that. 4 fingers follow the B, which is going to the right. So that means your palm is facing upward.
Yeah.
Which means the force is like up the page, right?
Mm-hmm.
That's how I understood it. If it makes sense to the person who explained it, that means we're on the same page. Okay, cool. Someone else on number 2, section 2, since here we're looking for the magnetic field, right? So number 1, can we try number 1? Somebody try number 1? You can raise your hand also, Any volunteer?
It says F. Do we just wait, Mr. Akhmedov? It says F. Do we just use B instead of F and just substitute at the end again?
No, you have to follow the same thing, meaning that 4 fingers represent the field lines. So you have to figure out which way the field lines will be going in this case.
Oh, okay.
Okay. So we're not switching anything. We're not assigning different digits for different quantities. So any volunteer? We have 31 people. Can someone volunteer?
Is it going into the page?
Mira, go ahead. Could you try to explain? I'll try to follow your explanation. Mm-hmm.
Because the force is basically perpendicular to the palm, so you have to face it towards the right.
Mm-hmm.
And V is down, so your thumb goes down. So then B would be going, the magnetic field would be going into the page.
Like that, right?
Yeah.
Thumb is down, force is out of your palm to the right, and four fingers go into the page. Does everybody follow that pattern? Yes? No? Maybe so?
Yes.
Okay, and someone try number 3, please. Dragus, you want to volunteer?
Yeah.
Go ahead.
If the velocity is going away from the page, then our thumb should be pointing at us, and our palm should be pointing to the right. Our palm should be pointing to the right. So if if you do that, it's kind of weird. It's kind of awkward, but your fingers should be going down.
Down the page, right? Am I showing
Yeah.
it correctly? Something like this? Down the page?
Yeah.
You can see it, right?
Yeah.
Thumb is this way, and forces to the right. So in this case,
Yes, I
maybe
think.
some of you will prefer like this kind of orientation. I'm not comfortable with that. Somebody can be more comfortable with that. Okay, so we can try maybe 2 more. Number 5, someone else? Shuhei, maybe you want to try? Shuhei.
Number 5?
Yes, number 5 in the second section.
All right. Wait a second.
You can think out loud.
Oh, so find a.
So we're looking for the field, right? We're looking for where would your 4 fingers be pointing.
Yeah.
So just follow the V.
I would well, would it be going to the right?
How do you know that?
The force is going to the left with the velocity, right?
Hold on a second. Force is not going with the velocity. Force
Oh, no.
is coming out of the page. So basically, usually we put the little dot there. Dot means like it's pointing at us out of the page.
Right.
So that's the force. Then which way is your thumb?
My thumb is going to the left.
Yes. So if you point the thumb to the left, 4 fingers should be, palm should be facing you out of the page.
Right. Right.
And then?
And then wait, sorry. Could you, my mom is kind of yelling. Could you like, what?
Okay. James, you had a question, but I think you got something wrong. Can you take over?
Okay, I'm sorry.
Okay.
Yeah, it's going up.
Okay, let's try to think about it. So James had a question, and he corrected himself. James, could you contribute to this part now?
So the force is heading out of the page, and your thumb is going to the left, so your fingers should be facing down.
Right. Shuhei, do you see this? Is my camera on? Yes.
Yeah, I see it. Yeah. Yeah.
Right. So thumb is pointing to the right. Palm is facing you, which should be like the force should be coming out of the page, right? You can rest your hand on the paper if you want, and then basically the force coming out of your palm in towards you, and then you automatically find 4 fingers should be pointing down the page. Okay, Shuhei?
Okay, thank you.
Okay, and number 3. So we have no time left. Maybe one person. Let's try number 3, section 3, question 3. Someone else. Jenny, maybe?
Yes, hello.
Hello. Number 3.
Hello. Okay, so you're pointing your thumb in the direction of the force, so your thumb would be pointing to the left, And if you're curling your fingers towards the bottom, that means that the force is, oh wait, no, the velocity would be going in the paper.
Into the paper, right?
Yeah.
Okay. Let's try it. Well, let me try if I understand. So force is going that way. That way, right? So the four fingers go down this way, and the thumb is going into the paper, which means velocity will go into the paper. Okay. Yeah, that's perfect. Are there any questions? We're gonna wrap it up. Are there any questions? Okay, so please practice a little bit more with the right-hand rule if you didn't finish the whole worksheet. Watch the video that I posted about Michael Faraday, and we'll meet up tomorrow. Okay, I'm gonna be closing this room. See you all tomorrow. Bye-bye.
Bye.
Bye.
Bye. Bye.
Yeah.